All right. This is actually my favorite. There's a lot of cool models. This is one of my favorite models, the logistic model. It's heavily used for modeling populations and the spread of diseases, which has been kind of a topic of interest recently, at least. Like a lot of times when we talk about populations, we say, "Oh, populations have exponential growth," but the reality is that they don't. If there's enough food and if there's enough space, then populations grow exponentially. But in reality, what happens a lot, and not just people, but like animals and stuff like that, what happens is that they grow exponentially for a while, but then, like, eventually they run out of food or there's too many predators or whatever, something happens, and then they actually start decaying. And in a logistic model, there's a horizontal asymptote, which has to do with the carrying capacity of something. So like, maybe we put some fish in the pond and the fish are breeding pretty quickly, exponential growth, but eventually there's just not enough room in the pond, or there's too many fishermen, or there's not enough food or whatever. And that's the logistic growth model. Okay. And that's what we're going to talk about here. The logistic model N of T. Whoa, something just weird happened right there. N of T equals C divided by 1 plus A e to the negative bt. That's not the prettiest, but it's certainly not the messiest either. Trust me on that one. There's plenty of uglier models. Logistic growth model, N of T, models exponential growth. Nope, that's not it. Exponential growth with something called carrying capacity, C. All right. So let's do some exploration. Let's look at some exponential growth formulas. And I forgot to pull this up too. If we do that, let's look at a a logarithmic growth model. Let's look at this one. Maybe 23082 divided by 1 plus 23081 times e raised to the negative 0.05 times t. Let's use this. Let's look at this model. This model is a model that I created to model how COVID or something would spread in my old town in Wyoming. All right. And so t is given in days here, or we're using x's. So if we're looking at days, let's, maybe for the x-axis, maybe let's look at a month. If we started with one sick person, it grows exponentially. But, there's only one sick person. But after a month, there's still going to be about 30 people who are sick now. What if we look at 2 months? Up to 60 days. After 60 days, oh, wow, now it's growing even bigger, right? We're going to have to zoom out a little bit to see after 2 months. I have to zoom out some more to see 2 months. After 2 months, wait, did I have the 1 month wrong? I did. 1 month, there's still only 5 people who are sick. After 2 months, there's like 20 people that are sick. And again, if we just look even more, look at this exponential growth. That's how diseases spread. Diseases spread, exponential growth. Oh my goodness, that's shooting up so high. Let's look at a year. Maybe up to a year. All right, we're gonna have to have a higher Y value. Maybe a Y value of 1,000. Nope, that's not it. A Y value of 5,000. Nope, that's not high enough. 10,000. Nope. 20,000. That's getting closer. Look at 30,000. If there was one sick person at the start, we have exponential growth. But eventually, everyone's gotten sick. And this is what we didn't want to happen with COVID, because this is way too steep right here. And there's just not enough resources to take care of those people. But just a disease in general, if nothing was done, would eventually infect basically everyone, right? Like we've all gotten the common cold, which is not the same disease, for example. That's kind of how, I mean, one common cold is not the same as another common cold, but that's getting into something else. This is how we model it. It's an approximation. Okay. And the carrying capacity is that horizontal asymptote. In my town, there were about 23,000 people, which means that that was our carrying capacity. So according to this model, then yeah, after about a year, basically everyone's got it. Everyone has gotten it. You can also think of this as population growth, and we're going to be doing one of each. Let's do some examples. Whoa. Example 4. So I looked at some of the COVID data in Wyoming, where I used to live before moving to Washington State, and I actually found a model, which we'll again talk about how to find that model in the last video of this section. I found a model, a logistic model for that, and a model for the cumulative confirmed COVID-19 cases in Wyoming is, and this was, yeah, I generated this model myself, a homegrown model here. N of t is equal to 57,8759 divided by 1 plus 250 e to the negative 0.02 t. Sorry, 0.019 t. This is a real life model that models real data. Okay. Where N is number of people who have received the disease, and T is the number of days after August 2nd, 2020. Okay, so this was the original surge in Wyoming. Well, maybe a little bit after the original surge in Wyoming, but not the Delta or the Omicron or whatever else might come after I recorded this video. That's our model right here. Let's ask some questions about it. Part A. And actually first, let's visualize this model. Let's graph this with Desmos. Let's type in these numbers. The numerator is a big number, although in context of population, it's not that big. 578,759. Our B value, or sorry, our A value is 250, and our B value is 0.019. Now we're looking at all of Wyoming, so of course the numbers are going to be bigger than just my own town. Let's make our y-axis bigger. There we go. This is kind of what this is looking like according to the model. Again, we did not actually get this much infection, which was good, but this is what the model predicted, at least for short-term change. And then again, there were measures that were taken in place to reduce this coefficient, isolation, eventually a vaccination and stuff like that. But if nothing happened and people just went around their day-to-day lives pretending there was no pandemic, this is what the model would predict. Okay. Part A wants to say approximately, part A says, sorry, what is the significance of this number in the numerator? Well, if you don't know much about the state of Wyoming, and let's be honest, most people don't know much about the state of Wyoming, you might not know. Well, let's combine this. Let's collect this with what C represents. C is that numerator. C is the carrying capacity. C is that asymptote. That asymptote is a line y equals C. C is the maximum population, or in terms of disease, the maximum number of people who can get it. Yes? So yes, this is the carrying capacity, but also that's how many people are in the state of Wyoming. Okay, that's less than Seattle, I'm pretty sure. So you can answer in two ways, right? Or population of Wyoming in 2020. There's not a lot of people in that state. It's the second least densely populated state after Alaska. It is the state with the fewest number of people, period. All right, let's do part B. Approximately, it's a cumulative cases, so approximately how many people have had COVID in Wyoming by November 3rd, 2020. And I'm going to tell you that this is a t-value of 93. So November 3rd is 93 days after August 2nd. Well, all we have to do is just plug into the formula. Okay? Just plug in 93 into this formula and get an approximation that way. And again, graphically, what you can look at that is that's when x is equal to 93. So graphically, we look at it right here. 13,241. Let's round to the nearest person. 13,241 people. Out of the population of about 600,000 by November 3rd, it was predicted with this model that it'd be about 13,000. It was actually 12,300. The actual data from the CDC for confirmed cases by that time was 12,399. So in actuality, we did a little bit better than was predicted, which is nice. Okay. Part C says, how about if B equals negative 0.005? What if we change that B value? B is how steep this thing is. Let's visually look at changing B values. Okay, before we even answer this question, right? What if this is about 0.02? What if I double this B value? Look at the difference doubling that coefficient makes and how many people are sick just 3 months later. It's exponential growth. That has a huge, huge impact if we double that rate. Right? Our estimate was about 13,000, but if we double it, it becomes 82,000. This B value has a huge impact on the rate of change, huge impact on the steepness of that curve, which is what everyone was always talking about when they said flatten the curve. Okay, so specifically it wants us to know what happens if that B value is 0.05. What if that B value was much lower? Well, then there would only be 3662 people with that case. We made that B value smaller. Look how flat that is. That would be great. 3662. All right. And that's what we have going on here. But let's go on a happier note and do an example about fishes. And that'll be the last example. This video will hopefully not be as long as the last one. Looking at population of fish in a lake after they were populated after T months, cannot write today, is given by this approximation formula. P of T equals 1,000 divided by 1 plus 19 e to the negative 0.1 times T. Part A wants us to graph P of T. We're not going to be graphing these by hand. Okay. So you can graph these with Desmos and just kind of copy down a graph onto your own paper. Okay. So let's graph this function and find some a good way to graph it. So our numerator is now just 1,000. Our B value is 19. Sorry, that's our A value. Our B value is 0.1. All right, so we're gonna have to change our scale. Let's find a scale that makes sense here. T is the number of months. So 360 months, probably not what we're looking at. Maybe let's look at a year, 12 months to start off with. And 300,000 doesn't make sense. The carrying capacity is 1,000 here. Carrying capacity is that numerator. It's that asymptote. So we probably don't want to look at anything bigger than that. Wait, did I copy this problem down right? 1,000 divided by 1. Oh, no, I didn't. I have a 219 as my A value. Okay, so this is what's happening. Okay, so after a year, we don't actually see that much growth. Let's look at maybe 3 years. All right, 3 years, we see a little bit more. We see exponential growth, and we can see it start to slow off. So that's how we're gonna kind of graph it like this maybe, or we could graph even more. It doesn't tell us exactly how many years. Graphed 4 years, that'd be 48 months. Yeah, that tells us a good amount more. We could graph it however we want. So we're just gonna copy 500 and 1,000 on the left. Say this is 500 fish. This is 1,000 fish. And we'll count by tens on the bottom. Say this is 10 months, 20 months, etc. And just kind of get a little picture. So our y-intercept is at 50. Very small. Let's graph in red. Then after 10, we're at about 125. We're about a quarter the way to 500. After 20, we're a little bit more than half the way to 500. After 30, we're a little bit over 500. After 40, we're about halfway to 1,000. And at 50, we're about 4/5 the way to 5,000 or to 1,000. And so we have this asymptote up here, asymptote at the carrying capacity. And then it starts off like exponential growth. And then it starts leveling off, kind of like that. What's important is that you know how to get the relevant information from Desmos, get a good scale, and be able to copy it down effectively. Look at part B. What is the initial population of the lake? Now notice, when I introduced the logistic growth model, I didn't tell you the initial population. Right? If we have a nice formula like this, initial population is A0. It's super easy. But for logistic growth model, it's actually not so easy. Right? This is our function. 1,000 divided by 1 plus 19, e to the negative 0.1 t. It turns out that none of these are the initial population. Well, if none of these numbers are the initial population, how do we find it? Well, initial, it just means t equals 0. So that's how we're going to solve this. What happens when we plug 0 into this equation? E to the 0th, any number to the 0th is 1. This just becomes 1,000 divided by 1 plus 19. Or 1,000 over 20, which is 50. We could also have gotten that from the graph, right? We said looking at this, the y-intercept is also 50. So originally, we had 50 fish. Part C, what is the population after 6 months? Well, we look at our model. 6 months is when t is equal to 6. Just plug in 6. Again, that's 1,000 divided by 1 plus 19 e to the negative 0.1 times 6. Type that into a calculator. Or, again, you could plug in 6 into Desmos and get about 88 fish, round to the nearest fish. They're not growing that fast. Lots of people fishing in this lake, maybe. When, this one's a good tricky problem. When will the fish population be 900? So this is asking for a y value. When is p of t equal to 900? So it's asking about a y value. It's asking us to find t. But you can also use Desmos for that. But instead of x equals, you do y equals. Figure out when it intersects here. But I want to show how to do this by hand too. That's when the population is 900. You're going to have to solve this exponential equation for t. How do we solve exponential equations? We get the exponential function by itself. But the exponential function is in the denominator. Anytime we have a variable in the denominator, we multiply by the LCD. And our LCD here is going to be this. It's just the denominator. Multiply both sides of this equation by the denominator, because then the fractions go away. That's going to give us 1 plus 19 e to the negative 0.1 t times 900 equals 1,000. You can either distribute or divide. We divide both sides by 900, and we get 10 over 9 over here. We get that. We keep on getting that exponential function by itself. Keep working on it. Subtract 1 from both sides. 10 ninths minus 9 ninths is 1 ninth. Divide both sides by 19. When dividing by 19, that's 9 times 19. That's 171, I think. Yeah. And then take the natural log of both sides. Side note, you could simplify that right-hand side. That's the negative natural log of 171. T is going to be the natural log of 1 over 171 divided by 0.1. I really tried to fit this on here. It didn't quite fit. Type this into a calculator. Should get the same thing. The natural log of 1 over 171 divided by negative 0.1 is 51.42 about months. And again, we should get the same thing with Desmos. 41 months. That's the logic to solve an exponential equation like this. Get a little good review for 6.6. I'm looking at the timer. It's not getting that. It's not going to be that much shorter than the first video. Last problem is really quick though. What is the carrying capacity? Carrying capacity is just that C. Just that numerator. It's that asymptote. saying if we give the fish long enough, how much fish will there be eventually? If we give them long enough, well, eventually they're going to get really close to 1,000 fish in this pond, in this lake. Okay. And you can see that on Desmos as well. Eventually, right? This is after 78 months. After 99 months, we're getting close to 1,000 fish. All right. That's the logistic growth model. It's very cool. Newton's law of cooling comes next, which is also cool. Have a good day. Let me know if you have questions.